Roorkee, KVEC, Makot, and MSEC. The 4-day event electrified the audience with 11 expert talks on wide-ranging topics, 3 workshops, 3 open house discussions with students, and a very insightful panel discussion. In March of 2020, we were proud to have placed 2 of our BTech graduates in Synopsys, a world-leading semiconductor company, for a full-time position. We are also proud to have our graduates working in other leading semiconductor companies such as ST Microelectronics and Micron through our close partner Sivya Multimedia. In September 2020, we collaborated with Boston Microtechnology to develop analog intellectual property blocks for a high voltage power management integrated circuit. The chip is fabricated using a 180 nanometer CMOS technology by XFAB, Germany. In 2019, another extension to the advanced VLSI was added, a fully operational industry-grade characterization lab capable of industrial-grade temperature characterization up to 1 part per million accuracy, a capability only few colleges in the world are capable of. Use of industry-standard test and automation tools such as LabVIEW, LabC Windows, and Python. Advanced VLSI Lab was set up in 2012, an initiative by Department of ECE and AEI in collaboration with Sankalp Semiconductor. Primary objective: to bring our VLSI academic framework closer to the industry and prepare engineering graduates for the challenges in the industry. Conducted industry-grade trainings in the VLSI domain. First major research and development activity resulting in a fabricated chip in a 180 nanometer CMOS in collaboration with Sankalp Semiconductor Private Limited and NIST Berhampur, Odisha. Funded by India Chip Program 2016. State-of-the-art information and technology and computing infrastructure with enterprise-grade electronic design automation, that is EDA tools from Cadence and Mentor Graphics, along with open source EDA tools. NDA in place with major semiconductor fabrication founders in the world, giving access to state-of-the-art IC technologies for fabrication. Industry collaboration with major semiconductor companies and skill development institutes to bring world-class research and development experience and industry-grade skill development programs to the engineering students at Silicon. An indigenous, fully in-house chip was designed by 12 undergraduate students in 600 nanometer CMOS technology, fabricated by XFAB, Germany, and fully tested for functionality and performance. In 2019, an extension to the advanced VLSI was added to provide a modern office space environment for industry training and research development work. The lab is equipped with fully networked workstations and AV equipment for fully functional local and remote office environment. In December of 2019, we furthered our goal of bridging the gap by bringing the industry closer to academia. Conducted NES-2019, a 4-day workshop, Nanotechnology and Embedded Systems. Eminent speakers from the top semiconductor companies and industries including Synopsys, STM Microelectronics, Sivya, VSD, VLSI experts, Tufts University, IIT Kanpur, IIT Kharagpur, IIT Roorkee, KVEC, Makot, and MSEC. The 4-day event electrified the audience with 11 expert talks on wide-ranging topics, 3 workshops, 3 open house discussions with students, and a very insightful panel discussion. In March of 2020, we were proud to have placed 2 of our BTech graduates in Synopsys, a world-leading semiconductor company, for a full-time position. We are also proud to have our graduates working in other leading semiconductor companies such as ST Microelectronics and Micro through our close partner Savvia Multimedia. In September 2020, we collaborated with Boston Microtechnology to develop analog intellectual property blocks for a high voltage power management integrated circuit. The chip is fabricated using a 180 nanometer CMOS technology by XFAB, Germany. In 2019, another extension to the advanced VLSI was added, a fully operational industry-grade characterization lab capable of industrial-grade temperature characterization up to 1 part per million accuracy, a capability only few colleges in the world are capable of. Use of industry-standard test and automation tools such as LabVIEW, LabC Windows and Python. Advanced VLSI Lab was set up in 2012, an initiative by Department of ECE and AEI in collaboration with Sankalp Semiconductor. Primary objective: to bring our VLSI academic framework closer to the industry and prepare engineering graduates for the challenges in the industry. Conducted industry-grade trainings in the VLSI domain. First major research and development activity resulting in a fabricated chip in a 180 nanometer CMOS in collaboration with Sankalp Semiconductor Private Limited and NIST Berhampur, Odisha. Funded by India Chip Program 2016. State-of-the-art information and technology and computing infrastructure with enterprise-grade electronic design automation, that is EDA tools from Cadence and Mentor Graphics, along with open source EDA tools. NDA in place with major semiconductor fabrication foundries in the world, giving access to state-of-the-art IC technologies for fabrication. Industry collaboration with major semiconductor companies and skill development institutes to bring world-class research and development experience and industry-grade skill development programs to the engineering students at Silicon. An indigenous, fully in-house chip was designed by 12 undergraduate students in 600 nanometer CMOS technology, fabricated by XFAB, Germany, and fully tested for functionality and performance. In 2019, an extension to the advanced VLSI was added to provide a modern office space environment for industry training and research development work. The lab is equipped with fully networked workstations and AV equipment for fully functional local and remote office environment. In December of 2019, we furthered our goal of bridging the gap by bringing the industry closer to academia. Conducted NES 2019, a 4-day workshop, nanotechnology and embedded systems. Eminent speakers from the top semiconductor companies and industries including Synopsys, STM Microelectronics, Savvia, VSD, VLSI experts, Tufts University, IIT Kanpur, IIT Kharagpur, IIT Roorkee, KVEC, Makot and MSEC. The 4-day event electrified the audience with 11 expert talks on wide-ranging topics, 3 workshops, 3 open house discussions with students and a very insightful panel discussion. In March of 2020, we were proud to have placed 2 of our BTech graduates in Synopsys, a world-leading semiconductor company, for a full-time position. We are also proud to have our graduates working in other leading semiconductor companies such as ST Microelectronics and Micro through our close partner Savvia Multimedia. In September 2020, we collaborated with Boston Microtechnology to develop analog intellectual property blocks for a high voltage power management integrated circuit. The chip is fabricated using a 180 nanometer CMOS technology by XFAB, Germany. In 2019, another extension to the advanced VLSI
Good afternoon, everyone. So we're going to start in another 10 minutes. In the meantime, you can enjoy the video and I'm also going to play one more video so you can enjoy that particular part. I hope you guys can able to hear the video voice. Okay. Great. I think we are almost ready. And I think Sarosh sir, I think you are co-host now. Okay, guys. So there are a lot of people. They have switched on their video. So I would say, just interest of bandwidth, if you can switch off your video, that will be too good. And Yeah, I know nothing is audible. It will come. So I can see a lot of people, all of you guys are saying nothing audible. So you just give us a couple of minutes. Yeah.
Advanced VLSI Lab was set up in 2012, an initiative by Department of ECE and AEI in collaboration with Sankalp Semiconductor. Primary objective: to bring our VLSI academic framework closer to the industry and prepare engineering graduates for the challenges in the industry. Conducted industry-grade trainings in the VLSI domain. First major research and development activity resulting in a fabricated chip in a 180 nanometer CMOS in collaboration with Sankalp Semiconductor Private Limited and NIST Berhampur, Odisha. Funded by India Chip Program 2016. State-of-the-art information and technology and computing infrastructure with enterprise-grade electronic design automation, that is EDA tools from Cadence and Mentor Graphics, along with open source EDA tools. NDA in place with major semiconductor fabrication foundries in the world, giving access to state-of-the-art IC technologies for fabrication. Industry collaboration with major semiconductor companies and skill development institutes to bring world-class research and development experience and industry-grade skill development programs to the engineering students at Silicon. An indigenous, fully in-house chip was designed by 12 undergraduate students in 600 nanometer CMOS technology, fabricated by XFAB, Germany, and fully tested for functionality and performance. In 2019, an extension to the advanced VLSI was added to provide a modern office space environment for industry training and research development work. The lab is equipped with fully networked workstations and AV equipment for fully functional local and remote office environment. In December of 2019, we furthered our goal of bridging the gap by bringing the industry closer to academia. Conducted NES-2019, a 4-day workshop, nanotechnology and embedded systems. Eminent speakers from the top semiconductor companies and industries including Synopsys, STM Microelectronics, Savia, VSD, VLSI experts, Tufts University, IIT Kanpur, IIT Kharagpur, IIT Roorkee, KVEC, Makot, and MSEC. The 4-day event electrified the audience with 11 expert talks on wide-ranging topics, 3 workshops, 3 open house discussions with students, and a very insightful panel discussion. In March of 2020, we were proud to have placed 2 of our BTech graduates in Synopsys, a world-leading semiconductor company, for a full-time position. We are also proud to have our graduates working in other leading semiconductor companies such as ST Microelectronics and Micron through our close partner Savia Multimedia. In September 2020, we collaborated with Boston Microtechnology to develop analog intellectual property blocks for a high voltage power management integrated circuit. The chip is fabricated using a 180 nanometer CMOS technology by XFAB, Germany. In 2019, another extension to the advanced VLSI was added, a fully operational industry-grade
So Saroj sir, somehow the voice is cracking a lot on your side. Looks like better now.
Is it better now?
Yes, 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 sir. 100%.
Okay. So let me now. How about now?
Yes, sir. Initially, it was like in a robot.
Yeah, yeah. So sometimes when the first time it's switched on, it sounds like that. Okay. So let's see if Steve, can you hear me now or?
Yeah, we should do the voice check of Steve also.
I see him unmuted. I see your video, Steve. Yeah, I think he's going to join in. Maybe he had an audio issue.
So all of you, this the session is on the live right now. So just in case there is any internet connection and you don't want to join the Zoom, maybe you can go in the VLSI Expert YouTube channel, and there you can just access this. The whole session is a live session.
And Puneet, maybe we can put the YouTube link on the chat channel as well.
Yeah, I can do it. So guys, just give me 1 second. Okay, so I just did it. So you guys can try also. And maybe it's, I think Steve is now online. Yes, we can see Steve. Hi, Steve.
Hey, Steve, can you hear us?
Yeah, you are on mute, Steve.
Yes. Oh, please allow unmute. You have to allow him, Satish. Please. Steve.
Wait a minute. Actually, he joined once again. That may be one of the reasons. Sorry, Steve.
Yeah, sorry, Steve. Just 1 second.
I just did it. I did it.
Okay.
So now he can unmute himself. Steve, now you can unmute yourself.
So Steve, you're on mute, but we still can't hear you. Oh. Yeah. Yeah, Steve, I think we can hear you now. At least.
Okay, so this is just through my laptop. Let me see if I can get headphones working. Are these working?
Yeah.
Yeah, that works great.
Let me just test these. Is this working?
Yeah, this works good.
Okay. So I don't know what happened with my regular headphones. I use them all the time.
Yeah, we can see you online unmuted, but we just can't hear you.
Okay. Well, looks like we're working now.
Okay.
Should I get started?
All right. Yeah, thanks a lot, Steve, for getting up in a cold morning for us to give this great workshop. So yeah, we'll get started. So our next speaker is Steve Hoover. He's the founder of Redwood EDA in Shrewsbury, Mass. One of my favorite places in Boston area. Good Indian food, but don't miss the cold.
True.
So he's founder of Redwood EDA, an early stage startup focused on next generation design methodology. With Steve is fostering an open source hardware ecosystem by providing the Makerchip online ID, which I think you're going to use today for the workshop, the WARF V5 CPU core, and the first class cloud hardware acceleration framework. He actively contributes to the TransactionLevel Verilog, TL-Verilog language specification, and delivers commercial TL-Verilog development tools. As an engineer with DEC, Compact, Intel, Steve designed components for Alpha, Itanium, and x86 server CPUs and network architectures. So Steve holds a BS, Bachelor in Science in Electrical Engineering from Rensselaer Polytechnic, and MS in Computer Science from University of Illinois, Urbana-Champaign. So Steve, please take it away.
All right. Thanks, Saroj, for the introduction. Happy to be here today. Hopefully my screen is sharing now. So you're going to get a chance today, as Saroj said, to do some very hands-on learning with TransactionLevel Verilog, learning modern design technology. So I'm going to start off introducing the platform that you'll be using. So this is makerchip.com. And then I'll step back and just talk in general about the role that abstraction plays in the design process. We'll take a high-level view. And then you'll get to jump into Makerchip and do some very simple hands-on learning, some simple logic circuits, get a feel for the platform. And then I'll talk about some of the more advanced things that we won't get into, just to give you a feel for other things that you could be following up with. So let me jump into Makerchip platform and just give you a little bit of a live demo. And let me also make sure that I have my chat up so I can see if there are any issues. I lost that window. All right, well. So for this workshop, we have a lot of participants. So I've started a bunch of extra servers. My server doesn't automatically scale. So just to make sure we can handle the load, I've started servers at NES 1 through 4. So I'll start on NES4, makerchip.com. And if you'd like to go to one of those servers yourself, so just to sort of partition the load, we'll partition everybody by the month that they were born. So if you were born in January through March, you can use NES1 and so on. So I've jumped onto NES4 just to give you a quick little demo of the platform. So inside Makerchip, Makerchip is an IDE where you can do circuit design with support for TransactionLevel Verilog. So you've got your window where you can do your coding. You can partition your workspace as you like. That code will compile and generate a logic diagram for you. This one's rather degenerate, so let's find something a little bit more interesting. Let's open up one of these tutorials and open up some starting code. So I've loaded that code into my editor by clicking the button, and that has generated for me a logic diagram of this circuit. And it's also generated a simulation of that circuit. So I've got a waveform viewer that I can navigate around. It's a fairly primitive waveform viewer, but it's got some nice integration with the platform. You can split your windows, so I can see the waveform together with the logic diagram, together with the code. There are actually two representations of the code. So I've got my source code in the editor. That code goes through the tools, and this is the tools interpretation of this logic. And you can see I've got some highlighting here on this signal. And if I hover over it, I can see that this value is used but never assigned. So I'll get some error messages here. I can also interact with this representation of the code. So if I click on a signal here, like this squared signal, it's highlighted in my logic diagram so I can understand the circuit, and it's highlighted in the waveform. So while I'm debugging this circuit, if I see something funny, this value doesn't look right, I can highlight this signal and see what's happening. Or if this CC value doesn't look right, where's CC in the diagram? It's over here, and here it is in the code. And if I click on the line number here, it's going to take me back to the source code. I can edit, fix the error, and then recompile. So that's a quick introduction to Makerchip. Trying to think if there's anything else I need to show here. I think that covers things pretty well at this point. I also want to show you, something more real, not just a toy example. And somewhere here, give me just 1 second. Okay, here. So let me show you an application first that was developed, I developed on the Makerchip platform. And we also have someone else on the call, Akosh Hadnoiji, who also contributed to this application. So this is, you can actually go here at fractalvalley.net. This is a Fractal Explorer program. And I'm going to just kind of zoom around this fractal a little bit. And you can see the screen's refreshing about once every second to let me navigate around this fractal, fly through. At the moment, this is rendering using C++. And if I click on FPGA, you'll notice the navigation is much smoother, much quicker. So what I've done is I've used Makerchip to design a logic kernel implemented on a field programmable gate array, FPGA. This FPGA is accessible in the cloud on Amazon infrastructure in the Amazon data center. And that FPGA can be used to render these fractals. So how did I develop that application? I developed the hardware kernel using Makerchip. So this is the source code implementing a fractal generator. It's about, basically it ends here, so about 170 lines of code. This is the circuit for it. And you can simulate and see the waveforms with all the calculations. It's a little tricky to debug the simulation from waveforms. This is the way we've been debugging for, I don't know, 50 years of circuit design. We've got a better answer that's accessible inside the Makerchip platform. And this is actually a feature that's kind of in alpha mode. So it's not really ready for prime time yet, but it is available. Just essentially undocumented, and the API needs a little work, but you can see the results of it. So this is what I use to debug my fractal generator. And this fractal is rendered based on simulation in the platform. The definition of how I would visualize my simulation is provided here in the remainder of the code. So about half of the code in my source is for rendering the fractal so that I can debug my design. So rather than debugging waveforms, a lot of my debug effort was started at this high level representation of my circuit simulation to understand how it's behaving overall, and then from there diving into the details of the waveform to understand at the signal level. So I've got my very high level representation of the fractal that the simulation is producing. You can see that currently in cycle 8, it's processing the second pixel, and I can zoom in on the calculation that it's performing to compute that pixel. The fractals are an iterative calculation. Every cycle I'm doing one iteration on the formula, and as I step in my simulation, I can see that it's focused on the next step in the calculation, and see that calculation in a way that's more meaningful than looking at the waveform to debug the math. Okay, so a feel for what you can do in the platform, and now I'm going to give you a chance. Actually, I'm going to start by giving some high-level perspective on TransactionLevel Verilog, and then let you guys do some coding inside the Makerchip platform. So, all right. So just some perspective on the industry in general, and especially on RTL design. RTL came into common practice around 1985. So this was the time of the 386 processor. And let me just ask you to kind of think in your own minds what you think the clock speed was for the 386 processor. versus clock speeds of modern processors. So I'm comparing this 386 design with a 2017 AMD EPYC core. 386 ran at 33 megahertz. Now we're running with clocks that are 100 times faster than this. So that means in the period of a single clock pulse in 1985, when RTL came into common practice, our clock pulse is 100 times. Let's look at transistor counts. So we all know about Moore's law. We all know about scaling. We all know it's exponential. But sometimes when you put real numbers to exponential curves, it's really a bit mind-blowing. So think in your minds what you think the scaling would be for transistors. Was anybody thinking 70,000 times? So in the area of a single transistor, essentially, in 1985, we can pack 70,000 transistors in that same area on silicon today. Right, so the point of this slide is that since 1985, since the introduction of RTL, the game has changed dramatically. We're facing completely different design challenges in, in 2020 than we were in 1985. So RTL was built to solve the wrong problems. TransactionLevel Verilog is one of the industry's solutions to this challenge. We're seeing today that the limit in design has more to do with the design methodology than anything else. The scale of the design, the number of engineers it takes to design a circuit today. And getting efficiency is all about abstraction. So we've been stuck at the register transfer level for a long time. TransactionLevel Verilog takes us to a higher level. So this triangle here represents complexity, and actually I've drawn it as a triangle, but it's really an exponential kind of a picture. So it's much, much, much wider at the bottom where you're looking at the device level details versus the behavioral specification. So TransactionLevel Verilog enables the focus of the design, and in particular the verification, to be at a higher level of abstraction, taking away the base of this pyramid, which, because of the exponential growth, represents a very, very significant level of detail, amount of detail. But in circuit design, the implementation, the physical characteristics of the design are extremely important. Much, much more so in general than in software. In software, you're, if you have a slow path in software, that slow path will contribute to the time that that code is executing. In hardware, every path in your circuit has to meet a particular timing. The timing of your entire design, your overall performance, is gated by the worst path only. And that's fundamentally different between hardware and software. So the details matter. You need to have control at the register transfer level as a designer. And TransactionLevel Verilog gives you that control through what are referred to as mappings or annotations that specify how your behavior is being implemented at the register transfer level. And you'll get a little taste of that today. This is a statement about both TransactionLevel Verilog today, as well as where the technology is headed down the road. And just another picture of this to highlight the fact that at the higher levels of abstraction in the design process, we have many, many different types of models, all connected to this golden reference RTL model. And as we introduce abstraction through transaction level behavior, not only are we making the modeling smaller, simpler, enabling verification to focus on a smaller, more abstract model, all of these various models, most of which are for verification, are in some way connected and overseeing the previously RTL model, now transaction level model. So by raising the abstraction, we're not only simplifying modeling, we're simplifying all the connections between these models. And the transaction level design is much, much more stable than the register transfer level. A lot of the design changes that will take place happen in these mappings. So a lot of the churn is absorbed here, and therefore doesn't impact all of these various connections into your golden reference model. All right, so it's not obvious that making a little bit a small jump in abstraction and stability of your model can have such a dramatic impact. This is why this methodology is so important. There are, competing directions to give us better abstraction in our design process. I'm not going to go into these in detail in the interest of time, but as general categories, the industry is very focused on high-level synthesis, C++ based modeling. Academia tends to be focused on domain-specific languages where you're implementing hardware design capabilities in an existing language. And transaction-level Verilog is a language that is designed for hardware from the start, whereas both of these approaches are leveraging advancements in software technology and applying them to hardware. Transaction-level Verilog is a hardware-first language. All right, so now it's your chance to jump into the platform yourselves. So as I said, we've got 4 servers up and running, NES-1 through 4, based on your calendar quarter, I guess, of your birth. Choose one of those 4 servers and open up NES Makerchip.com. And find my chat window here just a sec. So as you're doing that, in the chat, if you could just let me know if you have any trouble. As I said, many people are trying to access the servers all at once. There might be some slowness. If there is slowness, if it's not loading right away, please don't reload. It's not reloading because there are so many people on the platform at once. Just wait a minute. But I think we should be fine. And if you are, going through these videos after the fact, if this is pre-recorded, these servers are temporary servers. I'll be taking them down after the live recording. So if you're doing this after the fact, the load will be more distributed. You can just go to makerchip.com for these exercises. All right, so there's some mention in the chat about EDA Playground. EDA Playground is a similar platform. It does, in fact, have some support for TL-Verilog, but it's not as integrated into the platform. EDA Playground is really good for having access to industry tools so that you can test your code on industry tools, see how compatible it is across platforms without actually having those platforms installed yourself. All right, and I see Shivam is online. That's good to see. Shivam's very active in the community. Okay, so the exercise here is basically to reproduce this screenshot yourself. So just to get comfortable with the platform, I'll quiet down so you can just read through these steps. They're pretty self-explanatory. Hopefully seeing me go through the platform gives you a general idea of how to go through these steps. And once you have a screen that looks something like this, you're all set and we'll move on. So I'll just give you a couple minutes to go through that. All right, so I'll give you just a couple more seconds and then we'll continue. All right, so moving on, your first little getting your feet wet exercise inside Makerchip will be to create a simple logic gate. So here you'll create an inverter. Once again, these instructions are pretty self-explanatory. I'm trying to think if there's anything I need to explain here. I think I'll just let you read these and do this on your own. If you have any issues, you can bring those up in the chat window. All right, so I'm going to move on to the next one. If I'm going too fast, just speak up in the chat. Okay, so now moving on from gates to arithmetic, so operating on vectors of bits. So in the last one, and in fact, maybe I jumped a little too quick. So in addition to doing the inverter, maybe I'll give you another couple seconds here to try 2 input gates. So in Verilog, you have double AND, double OR that'll do AND and OR functions. You can provide 2 input gates to do those functions. And while you try that, I'll comment on these notes up here. So as you did these inside Makerchip, and maybe what I'll just do is really quickly jump out and just go through this myself to make sure we're all on the same page here. So NES some number makerchip.com, or I just jumped onto the main makerchip.com. So out equals in 1 and in 2. So this is going to give you a circuit that is an AND gate. And so you can see your AND gate here. And you know, what's one thing that's important to point out is in this circuit, if we go to the this representation of your code in the nav TLV pane, you'll see warnings on the inputs. These warnings say that you didn't drive these signals. On the output, you didn't do anything with this signal. Similar for the default signal that's provided here, reset. But we still got a simulation, right? So here's our waveform. We have random inputs, and we can see the output is the AND of those 2 inputs. So only if both of the inputs are high do we get a high output. And the log is also telling us that, oh, I guess it's just telling us we have a dangling input. So the platform has allowed us to simulate that anyway, and it's provided the random stimulus for us. So this, you know, it's a very simple feature of Makerchip, but it's a very powerful one. You can very quickly throw circuits together without worrying about the test bench and still see meaningful behavior to get some simple circuits going. Okay, so back to the slides here. So now trying out arithmetic functions. So you're going to operate on vectors. To specify a vector, you would specify the angle or the square brackets with a range. And here we'll make an adder, adding two 4-bit numbers to produce a 5-bit number. So go ahead and type this in and simulate that. All right, so just a couple more seconds with that. You can try other operators, you know, subtraction, multiplication, etc. All right, so I'm going to move on. One thing to comment on here, generally on the right-hand side, the ranges are not needed. You know, generally where you assign a signal, you're providing the bit range. In this case, we don't have assignments for these two inputs. That's the only reason we have the ranges in this expression. All right, so hopefully you were able to finish the adder. Now we're going to move on from combinational logic to sequential logic. In sequential logic, you have a clock. So basically sequential logic means clocked logic. You know, if you're looking at any digital logic chip, they all have a clock. The clock is the, well, okay, 99.9% of them have a clock. The clock is the timekeeper. It's sequencing your logic, which is why this is called sequential logic. In this example, we're going to look at a simple circuit that is computing the Fibonacci series. The Fibonacci series is a sequence that starts with two ones, and every number in the sequence is the sum of the previous two numbers. So we're adding 1 + 1 to get 2, 1 + 2 to get 3, 2 + 3 to get 5, etc. So every cycle in this design, we're going to take the previous two numbers in the sequence and produce the next number. And you can see that depicted here. So these little boxes here are called flip-flops. The flip-flop is the timekeeper. It's taking the clock input, which is represented by this little triangle at the bottom. We're not showing the actual clock wire, just implying that. So the flip-flop is responsible for watching the clock. When the clock has a rising edge, the value from the left side is brought through to the right side, and it's held on the right side until the next clock pulse. And during that clock pulse, the logic will evaluate. So these flip-flops are, at this time, as depicted here, driving a 3 and a 2 on these wires. The combinational logic, the adder, is evaluating to produce a 5, and that sits at the input of this flip-flop until the next clock cycle comes along. So we've got one clock cycle for this combinational path to evaluate. So one clock cycle for the values to propagate through this adder circuit. All right, and so the simulation now is going to you know, repeatedly compute the sum of the previous two numbers and produce a waveform that looks like this. All right, now there's one thing missing from this diagram, and that is reset. So we need something in our circuit that's going to start us off with these initial two ones. All right, so you know, once again, 99.9% of silicon that's out there also has a reset signal. The reset signal is responsible for getting the chip into a known state. So here we've added reset, and we're using this reset to initialize the circuit to hold two 1 values here and here. Right, so the protocol with reset is it'll be held high for you know, a fairly large number of cycles to let the silicon, to let the circuit stabilize to a stable state, a reset state. And then we'll deassert reset and let the logic run. And often you'll see that reset is a negatively asserted thing. So opposite polarity on the signal, but here we're using a positively asserted reset. So it's high during reset, low otherwise. So when we throw reset, we're going to have a 1 value here. The clock is running during reset. That allows that 1 to propagate here and here. And we'll get into this steady state of 1s. And then when we deassert reset, we'll start utilizing this path through the adder. Okay. All right, now you're, so in transaction-level Verilog, this circuit can be coded up like this. So we have a number that we're computing. So this is the expression for this number here. And so first, this mux. If you know, if you already know Verilog, or if you know C++, or I guess JavaScript is the same. Many languages use this ternary operator. So the ternary operator is this question mark colon, and this is used to implement this multiplexer here, which is selecting one of these two inputs based on reset. And the notation is to give the select signal first, the reset, then the if reset is 1, we're selecting the 1 input. Otherwise, we're selecting the result of the adder. So this parenthetical expression is the adder, and the adder is taking in inputs that are the previous value and the previous value. So in TL-Verilog, we're expressing the previous value using this ahead by 1 operator, and the previous value using ahead by 2. So unlike RTL, if you happen to be familiar with RTL, in RTL you would explicitly have code to create this flip-flop and explicitly have code to create this flip-flop. You would explicitly name the output signal of the flip-flop and the output signal of this flip-flop. In TL-Verilog, you don't have to do that. TL-Verilog has a property called timing abstraction. It's a particular form of timing abstract modeling. There are many different timing abstract forms of modeling. In TL-Verilog's timing abstract modeling, you assign num, and essentially that gives you an infinite number of staged versions of num that are accessible to you. Any that are used exist, any that are unused don't exist in your physical circuit, but logically, num exists for all of time, and you can reference that num at any any staged version of that num, and this is how we do it. So this single expression here gives us this this entire circuit. All right, and I'm glad I've got Shivam and Akosh online to answer questions in the chat while I talk. Makes it a bit easier. So now that you've seen that circuit, which I've represented here now on the right, just for reference, you get a chance to implement a similar circuit. So yours will be just slightly simpler than the Fibonacci sequence. You'll implement a free running counter. So this free running counter will start off with a 0 value during reset, and after we deassert reset, your counter will begin counting. So 1, 2, 3, 4. You can make your count 16 bits wide. And this is the circuit that you'll implement. So on reset, we want a value of 0. After reset, we want our count to take on the value of the previous count plus 1. Okay, so you can use, again, use this as a reference for the syntax. One important thing to note is that in TL-Verilog, indentation is always 3 spaces. TL-Verilog is a white space sensitive language. The indentation matters. And in this case, you would put your logic right under the TLV, within the TLV section, 3 spaces of indentation. End with a semicolon, and your expression should look very similar to this one. So I'll give you a couple minutes to see if you can implement this circuit. All right, looks like we have some folks that drank their coffee today. They're done already. But I'll give you a couple more minutes. All right, so while you're finishing up that exercise, I guess I can keep this up without obscuring this too much. Let's do it this way. So I'll type this as you do it yourself. In case you had any trouble, you can see what I did. Oh, I used count and num, so this needs to be count. That's weird. Oh, okay. I took away my reset signal, that's why. All right, so this should give us a counter circuit. Hopefully you guys have been able to produce this as well. Some of you, it looks like, faster than I was able to do it, so that's good to see. And we do indeed have our counter at this point. All right, so moving on. And so I think in the interest of time, I'm going to go through this very quickly. And Saroj, if you want to jump into chat, or anybody else who's running this, just to confirm, I think the intent is to wrap up at this point. But just to quickly, you know, one of the important aspects sorry, go ahead.
No, just go ahead. I think it seems like people are, on pace, so just go ahead with your point. So
okay,
good.
So when should I aim to wrap up?
I mean, it's pretty flexible. So you had 2 hours, so so you have like another 1 hour, 10 minutes.
Oh, all right. I misunderstood. I thought I had 45 minutes.
No, that was just for the talks. so yeah, so you can end it anytime or take question answers, Q&A. So that's
okay.
Been kind of the format. Most of it's going in Q&A. So yeah, you just go at your pace. That's fine.
Oh, okay, great. All right, so I have a lot more time than I thought then.
Yeah, no, you do.
Okay, good. So that'll give us a chance to get into a little bit more. That's great.
Sure.
All right, so let's talk about pipelines, which is to say timing abstract modeling. So what I'm depicting here is a circuit that's computing Pythagoras' theorem, right? So Pythagoras' theorem is telling us the length of this edge here, C, as the square root of a squared plus b squared. So this is that computation, right? So first we have to square a and b, then we have to add those together, and then we have to take the square root. So this is a fairly deep computation if I'm trying to implement this in a circuit, and I'm doing so in a setting that's running at a high clock frequency. I can't do this whole computation within a single clock pulse, a single clock period. So I have to split up the computation. So I'm splitting it here into 3 stages: the squaring, the addition, and the square root. So this is a pipeline. First stage of the pipeline, second stage, third stage. And the nature of a pipeline is that we can feed sources into this pipeline every cycle. On the next cycle, this computation will go to its next pipeline stage, and we've got another computation right behind that. So simultaneously, we're working on 3 different computations of Pythagoras' theorem in different stages of the computation. So this is the sort of RTL depiction of the circuit. When you think about this circuit in a timing abstract sense, in transaction-level Verilog, you would give yourself the context of a pipeline that has pipe stages, and you would put your logic into the stages of the pipeline. So we would have this mental picture of our circuit. You'll notice in the timing abstract representation of the circuit, I haven't drawn the flip-flops. Right, the flip-flops are implied by the fact that you have logic that's producing a value in one stage and consuming it in the next stage. So the syntax for expressing this pipeline in TL-Verilog is as so on the right. You can see a very direct correlation between the logic syntax and the logic diagram. Right. For those who are familiar with RTL, you know, this is the comparison between the transaction-level Verilog for this circuit and, excuse me, the system Verilog for the same circuit. There are many different ways to skin a cat in system Verilog. This is one industry recommended coding practice that that Intel tends to follow. There are different coding styles with different characteristics, but this particular coding style, you can see that, you know, as with any reasonable coding style in system Verilog, the TL-Verilog is much more compact for a pipeline design. So the compactness of the code is certainly a strong benefit. There are many studies that indicate that bugs are proportional to lines of code. So you definitely get a nice bug reduction from using transaction-level Verilog, which translates to productivity. But the main point of expressing your logic in this manner is not just the code reduction. It's about the ability to safely and easily make modifications to your design. So let's say, you know, we've started with this 3-stage implementation of our circuit, but we want to use this same, you know, this same computation in a design that has different constraints. So now we're getting on to sort of leverage and reuse benefits of using transaction-level Verilog. So in our new context, let's say our A value happens to be in one corner of the chip, and the C value that we're producing is in a completely different corner of the chip. So we need some time to get A to the place in the chip where B exists. So we have this dead cycle that's just transit wire delay. And then, you know, C is in a completely different corner, and we need another cycle of wire delay here. So to get from this circuit to this circuit is this change. And you can see the change is just to the stage bucketing of the logic, right? So we've taken this A squared computation and we've moved that from stage 1 to stage 0. And we've taken the square root and we've moved that to stage 4. And we do that just by changing the at designations. This kind of transformation where all we're doing is changing the staging in TL-Verilog for this simple circuit as well as for any circuit, no matter how complex it is. If you're just changing the stage bucketing, you are guaranteed to not be changing the overall behavior of your circuit. So this is a safe change to make, which I could show you if this would stop popping up. And so I know that by making this change, I haven't broken anything. Whereas in RTL, you know, the change is pretty significant surgery to your model. And I can't tell you how much of my wasted doing changes like this manually. That was a lot of the motivation for modeling in TL-Verilog. All right, some Q&A in the chat. Looks like questions are getting answered. So now you guys get a chance to implement your own pipeline circuit. So let me set the context for this one. Again, as you go through this coding exercise, I've provided for reference the example that we talked about for pipelining, the Pythagoras' theorem computation. This, so what you're going to code up would be some logic that would be part of a pipeline. We're not showing all of the computation that's being done in the pipeline. You're actually just coding a little bit of logic that's accumulating error conditions that might happen during a computation. So the computation itself is not shown. We're just looking at the accumulation of errors. So whatever computation happens to be being performed in this pipeline is producing a bad input, illegal operation, overflow, divide by zero. So whatever this computation is, as it's marching through the pipeline, these various error conditions are being flagged. And your circuit is simply accumulating those. So in stage one, we have these two error conditions. So we're going to accumulate those into a signal called error one. And then in stage three, we have another error condition being flagged. So we'll combine those. So each of these blue circles is combining error conditions, and it's going to combine them by ORing them together. So we're basically just ORing these four, but distributed over a pipeline. All right, so this error 2 is going to propagate forward and get combined with this divide by 0 to produce error 3. All right, if there are any questions about the nature of what you're trying to implement, you can speak up in the chat. Yep, so this exercise is to create this circuit. You'll know that your circuit is correct if you're able to produce the diagram that looks exactly like this. Doesn't matter so much what you use for the names of the inputs if they're hard to read, but you know, you want to create a circuit that's going to OR these conditions together. Okay, so I'm going to keep this up for reference for the syntax. Again, everything is 3 spaces. Your calc pipeline would be 3 spaces indented under your \TLV section of code, and or in this case, your comp pipeline. And go ahead and try that on your own. And while you're doing that, I guess I'll do it on my own so I can show you guys for comparison. So I'll give you about 5 minutes to go through that. All right, so I see a bunch of questions in chat. I don't want to get too distracted from the flow of the talk. You know, there's some questions about FPGA design and Xilinx tools for rerunning the Fibonacci series. I mean, these talks are going to be recorded. You can view them afterwards, go through again. There are examples inside Makerchip, and let's see if I can kind of fit this on the screen without obscuring everything too much. So let's leave it like that. You know, there's an examples page here, so you can pull up some examples, and there is a Fibonacci sequence example, so you can load from here and see the Fibonacci example that way. All right, so while you guys were coding, I coded this up as well. This is what I came up with. Looks like my circuit looks right. So you're specifying the logic within the stages that the logic exists. Your logic is all ORs. So I'm first ORing together these two inputs. Bad input, illegal operation. In stage 3, I'm combining an overflow with that OR from stage 1. So, you know, again, the main point here is I'm not explicitly staging the logic. I'm implying these flip-flops by the fact that I assigned error 1 in stage 1 of my pipeline, and I'm consuming it here in stage 3 of my pipeline. So that's giving me these two flip-flops. And then again, combining in the divide by 0 in stage 6, implying these flip-flops. Okay, so this is my complete code for this circuit, and giving us this logic diagram. And we should see that, you know, since we're not assigning these inputs, they're random with roughly 50% probability of asserting. That means the probability that we don't have any errors in our pipeline is pretty slim. So if we find the error signal, we should see that there's almost always an error, as there is. All right. So moving on. So the next concept here is a concept called validity. So validity tells us, and this is a concept that does not exist in RTL. Validity is a little bit of extra information about our circuit that you're able to convey as a designer to specify when the computation that your circuit is performing has meaning. If you look at the simulation of a real circuit and what that circuit is doing, you'll find that, you know, 90+ % of the time, most circuits aren't doing anything. The clock is running, the gates are always there, they're always producing output, but typically that output is meaningless, right? Even in your CPU, most of the time your CPU is sitting idle. Maybe it's doing some background tasks, but then you dive closer, you look at the execution units, the multiplier. Most of the time you're not doing a multiply, so that circuit is sitting idle. We have no way in RTL to convey that information, and that's valuable information in a number of ways. So in TL-Verilog, just going back to our Pythagoras' theorem example, we can convey the fact that we have a meaningful computation in the pipeline by using this question mark syntax, which is referred to as when. So we have a signal valid, that is our indication that we have a computation to perform. And then we use this when valid to express that the valid is, you know, to basically convey in our model that this valid signal is conveying that the circuit is doing something meaningful. So we apply that valid across the entire pipeline, and to basically say, all right, this pipeline has something to operate on. I guess the first easiest thing to look at is the impact on the waveform. So this waveform viewer here is not the waveform viewer inside Makerchip. I forget which waveform viewer this is, but you can see in this waveform where we're actually doing a meaningful computation, right? So it becomes, instead of just looking at a sea of numbers, it becomes very evident that we have this pipeline behavior and these signals are distributed over the pipeline, and it's very clear where we have valid computations being performed. So several benefits of being able to convey this information in your design. For one, looking at waveforms like this is way easier to debug. It's very obvious to me that the value here corresponds to the value, it's related to the same computation as the value here. I can see the pipeline nature because these invalid cycles sort of make that apparent. Your design is fundamentally cleaner. There's just more information in the design to work with. In particular, you get better error checking. So if I inadvertently were to consume a value that is known to be invalid, my tools can catch that for me. So this obviously leads to models that are more free of bugs and more stable. And the next benefit, maybe a concept that's new to many of you, is automated clock gating. So let me go to the next slide, which talks about clock gating. So clock gating is a power savings feature. In your circuit, basically you have this global clock. The global clock has to get to every flip-flop in your entire design. So this global clock distributes everywhere in your circuit. Distributing all of these clock pulses everywhere in your circuit burns a lot of power. And you can save a lot of power by only delivering the clock pulses that are needed where they're needed. And that's what clock gating is all about. So with clock gating, you'll have this global clock that distributes out to the clock gators. And the clock gators are identifying which clock pulses do I actually need. It's squashing the pulses that are not needed and producing this sort of subset clock that's delivered to the flip-flops that need that. So in the case of our pipeline, we have a computation going through the pipeline. Some of those computations are valid, some of them are not. The computations that are not valid, there's no reason to propagate their invalid values through a flip-flop. There's no reason to have a clock pulse corresponding to those invalid cycles. So when we do have something valid going through the pipeline, these clock gators are going to generate pulses for us, right? So these pulses would correspond to a valid transaction being carried from one clock stage to the next clock stage to the next clock stage. If the rest of the computations are invalid, there's no need for clock pulses. All right, so this is going to save us a lot of clock distribution power. So with this knowledge of validity, we can use this to know when we have data that needs to be propagated through flip-flops. So we can generate clock gating automatically from that information. This might be what an ASIC implementation looks like. In an FPGA, generally you would do, all the circuit, all of the, all of the gates that you have available are laid out ahead of time. It's a little awkward to create clock gators in an FPGA. Generally in an FPGA, you'll have flip-flops that support an enable capability. So that's basically saying the gating function is incorporated into the flip-flop cell. It saves less power, but is more feasible on an FPGA. So in an FPGA, you can configure the TL-Verilog tools to generate enable flip-flops. All right. So now you guys can try this out for yourselves. I should have warned you to keep the circuit that you had for your error pipeline. If you did not keep that up, you also can go to this validity tutorial and similarly go through that one. So this validity tutorial, once you scroll down and click on this, that's going to load the Pythagoras' theorem example and give you a valid signal to use. So very similar exercise. I apologize that I forgot to point out to hold on to your work from the last lab. But using the last lab, which again looks similar to Pythagoras' theorem, what you'll do now is convey valid throughout your pipeline computation. As we've done before, let Makerchip come up with the value for valid. You can just use it this way. So you'll add this when condition for valid, sorry, and then indent your pipeline calculation under that when condition. In Makerchip, you can indent by selecting this block of text and using Control right square bracket. That'll indent the block. So it should be a very quick thing to add the valid condition and indent your logic and recompile. And then, see what impact that has on both the logic diagram and the waveform. All right, so while you're doing that, I'm also doing this myself. It's in the process of compiling. So I do have my block diagram. All right. Just give you another couple seconds. All right, so you can see now in your block diagram that you have this new valid signal, and it's applied as a gating condition, a when condition on these various pipeline computations. And we can see in the waveform that we have gray values. So the way this is running inside Makerchip, we are computing the values when the computation is invalid, but we know that they're invalid. We're representing them in the waveform in gray. So we can very clearly see where there's meaningful computation. Okay. All right, so let's see. So it seems that I can keep going probably for another 15 minutes, half hour, something like that, which is longer than I was expecting to have. Let me just take a minute here to pull up a little bit more, because since we do have some extra time, it'd be really fun to get into a little bit more material than I put in the presentation. So let me just jump back to this in case anybody is still working on this one. Actually, I'm just going to go ahead and do this inside Makerchip itself, since that's a little bit more fun. All right, so inside Makerchip, there's some course slides here. There'll be more training material coming over time in the platform itself. And there are many other training opportunities for TL-Verilog, which I'll talk about after this part. But I wanted to talk a little bit about kind of the next level of modeling, right? So you've learned about creating a pipeline and pipeline computations, where you have a transaction marching through this free-flowing pipeline. What we're going to do next is take that concept beyond just free-flowing pipelines, and somewhere in this, so here, we'll take this beyond free-flowing pipelines into more complex flows through a microarchitecture. All right, and this is going to be a little bit awkward. These slides were meant to be an animation, and I don't have that animation inside of Makerchip, but that's okay. So, so far, we've been looking at a very simple transaction flow that is a free-flowing pipeline. And we've been looking at how we have transaction logic, so the computation of Pythagoras' theorem, for example, sort of conceptually off to the side and then dropped into this free-flowing pipeline. We can do the same thing in TransactionLevel Verilog with more complex flows, and this is where TransactionLevel Verilog gets its name. So here I have a depiction of a rather arbitrary microarchitecture, a rather arbitrary flow of transactions through machinery. But this logic might represent a some sort of a ring interconnect where you've got some computation, maybe a packet forming up the packet headers, and you're sending that ring from you're sending that transaction from one port onto a ring, around the ring to a destination port, and then doing some more processing and queuing of that transaction at its destination. So here we have a transaction going through a pipeline that supports stalling, getting dropped into a first in, first out buffer, issuing out of that buffer down another pipeline. This one is actually implemented as a phase-based pipeline with back pressure. I won't really explain what that means, but it's another flavor of pipeline that can be back pressured so that if the receiver is not ready to process any transactions, it can apply back pressure and things will queue up. Then the transaction has an opportunity to go around the ring to a destination port. If that transaction happens to be destined for the port it's already on, it doesn't have to take a hop around the ring. It can bypass through this arbiter. So the transactions, when they hop off the ring, will go through a short pipeline here, arbitrate with the local traffic, get queued up, and then issued out of this queue down a free-flowing pipeline. All right, so this is just our arbitrary microarchitecture to represent the fact that transactions can go through these various types of flow and queuing structures. So TransactionLevel Verilog lets us set up that microarchitecture sort of independent of the actual transaction computation. Right, so all of this setup for the transaction flow is agnostic to the particular transaction. And then we define the transaction. So this logic might be processing packet headers or performing Pythagoras's theorem computations or accumulating errors, whatever it happens to be. And then we take these combinational clouds of logic, and just as we did with our pipeline, by putting them under at stages, we place them into this transaction flow. All right, and that's represented here as these arrows specifying at which stage along this flow are we going to perform various computations on the transaction. So just to look, kind of next level at how this works. If we consider a scenario where we're looking at this cloud of logic here, this combinational cloud. There's a question in chat about RTL design done with TL-Verilog. Yeah, I mean, the example I showed earlier with the Mandelbrot Fractal Explorer was written in TL-Verilog, for example. I'll talk about other examples in a minute. Okay, but back to the slide. So if we're looking at this combinational cloud here, performing some computation immediately after the FIFO, and we look at what happens in the FIFO. So let's ask the question, what's actually going to exist in the FIFO? What signals are we capturing in the FIFO? The answer is any signals that are produced to the left of the FIFO and consumed on the right of the FIFO have to go through the FIFO. So the contents of the FIFO, the fields that exist in the entries of the FIFO, are defined entirely by signals produced on the left, consumed on the right. If I'm, just as we retimed logic in our earlier pipelines, if we have a timing issue with this combinational cloud that we don't have time in the cycle right after the FIFO to do this computation, we might, as microarchitects, want to solve that timing path by doing that computation prior to dropping that transaction into the FIFO. So we want to move this combinational cloud from here to here. All right, so it was here, and now we're rebucketing that computation to be performed here. So now the output of this combinational logic exists on the left. It has to get through the FIFO to be consumed on the right. And likewise, there might be signals that this combinational cloud is consuming that are no longer consumed on the write and no longer needed in the FIFO. So the tooling is going to take care of that for us. So we just need to take that combinational cloud and drop it into a different place in the transaction flow and let the tools take care of what actually needs to go through the FIFO to get to the other side. So the FIFO itself remains completely generic. It doesn't care what fields it's holding. It just knows it's getting fields from one side to the other, and the tools will take care of figuring out what those fields are. So very powerful mechanism. I thought I had one more point about that here. Maybe I missed it up front. Okay, I guess I didn't have that one in this slide set. But just as one more example to talk through without the picture. An example I often use is, and this comes from my own experience, where there are a lot of aspects of the microarchitecture that tend to get incorporated very late in the game. We talked about clock gating. That's one good example. Generally your clock gating is implemented as an afterthought to save power before you get your silicon out the door. And because it comes late, it tends to be very disruptive, right? The later you're applying a change, the more collateral there is from your design team around the physical implementation of your design. And then you go in and you add clock gating logic and things break. So what tends to happen very frequently is you'll have particular targets for your power consumption, and you'll have goals in mind that you want to meet some, you intend to clock gate this percentage of your logic to meet your power targets, but you defer all of that work until later. And then when later comes along and you're, pushed up against your deadline for taping out your silicon, you're trying to go back in and add your clock gating logic, and your managers are starting to get nervous about the impact that's going to have on your tape out date. And in the end, the decision is made, we're just going to live with a higher power than our original targets because we don't want to break things last minute. And then you never really implement the full clock gating. With TL-Verilog, since that clock gating is in your design up front, it's just always there, and you can continually refine it, so much less disruptive. That's leading me to this next example, which is a similar scenario where you also have targets for reliability. And so reliability, one aspect of reliability is that your circuits aren't perfectly reliable. In particular, you have particles from space that are constantly bombarding your silicon die. And we don't tend to think about these particles much, but when you're designing at such a small scale, this tiny little particle that came from space that just happened to whack your logic gate in your silicon can flip a bit in your silicon. And our design has to be resilient to that. So your design will have targets for reliability that require certain protection mechanisms to be in place. One example of that would be parity, where you look over all of the bits in a particular structure and XOR them together. And that gives you parity on those bits. So if you have 3 bits that are all 1 and you compute parity on that, 1 exclusive or 1 exclusive or 1 would give you a 1 bit. If something gets flipped, one of those 3 bits that are supposed to be 1 becomes a 0. That affects your parity computation. That would result in a parity of 0, and you would have a different parity. So if you carry that parity bit through a structure, you can recompute parity at the output and and use that to detect that a bit was flipped. So, let's say in our circuit we've implemented our design, it's been verified, we're ready to tape out, but our reliability engineers are coming back to us and saying, our design's not reliable enough, we need to add parity protection. So if we need to add parity protection to, say, the FIFO structure and the ring structure, we might do that by computing parity at this stage in our pipeline before the FIFO. So we'll look across all of the bits that are going into the FIFO and compute a parity bit and add that parity bit now to the FIFO logic. and carry that parity bit through the FIFO, through this back-pressured phase-based pipeline, through the ring, and you know, maybe as a good convenient point to check parity, we'll do that after the arbiter. So now we've got parity flowing through all of these structures, protecting all of these structures, so that at the output of the arbiter, I can check parity and detect whether I had an error. And this would protect us against single bit error flips. But the point of this example is the benefit of setting up this transaction flow is that we can add the parity computation, which is just an XOR over all of these inputs. We can add that to the FIFO, so that's, we don't even have to add it to the FIFO, actually. We just have to provide that expression for parity. And then at the output of the arbiter, we have another computation, recomputing parity, and comparing that computation, which is an XOR, with the parity that we computed back here. So two different parity computations at two different points in the pipeline, and a comparison between those parity bits. So just two very simple logic expressions to get added to the design to add parity. And the result of that is that the tools will recognize that we need the parity here that was computed back here and drag that parity through all of these structures for you. So all of this stitching through these structures, which could be hundreds of lines of code in RTL, are 0 lines of code in transaction level design, transaction level modeling. All right, the actual implementation of that mechanism is actually incredibly simple. It's simply a wildcard assignment. So instead of assigning a particular signal, you use a wildcard assignment that can be applied to any signal. And that's used to express the flow. So here in this slide, we're looking at an example that's implementing a back-pressured pipeline. So every stage of the back-pressured pipeline is basically just the ability to recirculate that value and hold that value in the flip-flop. So if you apply back pressure at the output, that back pressure is going to force recirculation where necessary and let transactions pile up in this structure. And we can implement that back pressured pipeline by implementing this recirculation mux, which is a expression that, you know, the mux we saw as a ternary operator. Here we're implementing that ternary operator. We're interacting between these pipelines, which because of the back pressure means these have to be independent, you know, pipelines, referring to the pipeline construct in TL-Verilog, which is a free-flowing pipeline. But anyway, directly translating this logic, you get this logic expression, and we use any so that this logic expression can apply to anything marching through this back-pressured pipeline. And then we can add our combinational logic, which, you know, might be Pythagoras' theorem computation, anything we want to do to operate on the transactions within that context. And the back pressure gets applied. So we can provide these generic components that provide the back pressured pipeline that know nothing about the transaction itself. We can put those in generic components and just instantiate a back pressured pipeline, for example, and then add into that context our transaction logic. So this is something that you just can't do with RTL. It's essentially impossible to create these generic components in RTL and then add into the context that they create your transaction logic. So I apologize that I didn't have, I have some better slides that explain these concepts, but I didn't have them handy since I thought the talk was shorter. This is what this back pressure pipeline would look like inside Makerchip in the block diagram. All right, so lastly, I'll go back to the presentation. Okay, so things that we didn't talk about yet in transaction level Verilog. So, you know, we sort of touched on this in the last example, but I didn't really explain how you create logic with multiple pipelines and interact between those pipelines. There's also a construct specifically for microarchitectural state. So we've looked at flip-flops in our design that one of the nice things that transaction-level Verilog does that RTL doesn't is it creates a clear distinction between flip-flops that are there to stage logic, as they do in a pipeline, versus flip-flops that are holding on to values, holding on to state. So there is a specific construct in TL-Verilog for state. It's not everything that I want it to be at this point. I don't always use it, but anyway, there is such a construct. There's support for hierarchy. So hierarchy is mostly about replication. And TL-Verilog has a much more convenient way of dealing with hierarchy than Verilog does. So luckily we did have time to talk about transaction flows. So, going through it kind of high level, but hopefully you got a good sense of the true power of transaction level design. And we didn't really talk about modularity and reuse too much, beyond my casual mention that you could put these flow components into library components, and hardware construction as well. So this is sort of in an exploratory form at this point in TL-Verilog, where we're using a macro preprocessor for hardware construction. But what I mean by hardware construction is, this is a term you'll hear a lot with domain-specific languages, with languages like Chisel and BlueSpec, where you're able to write programs essentially that are responsible for defining your hardware. So you're using a program to construct the hardware model that you want. I mentioned there were other training opportunities. So right now I'm putting together a lot of different training based on RISC-V. So I've got a couple different things. Currently I have a workshop that I'm running with Kunal Ghosh called the Myth Workshop that's getting a lot of attention. We've even recently, you may have seen some blog posts about first a 13-year-old, and then actually coming out today should be a blog post from RISC-V International about a 12-year-old who went through this workshop and designed his own RISC-V core in the workshop. The workshop is really not meant for students that age. It was a struggle for them, but still very significant that someone at that age was able to develop a RISC-V core. And then kind of variations of this course aimed more at hobbyists and at professionals. And, if you want to learn more, good places to learn beyond those workshops, as I mentioned, the tutorials inside Makerchip. So you can, we covered some of this. You can walk through these various tutorials and learn these concepts. These course slides come from a course on Udemy, which is a reasonably priced option as well. And various resources at, let me jump out of here. RedwoodEDA.com. There's some description of TL-Verilog examples and a lot of different blog posts and articles and training resources available under publications as well. So feel free to look through there. There were some questions on chat about verification. There's some verification focused topics here, some industry perspective, etc. Also, if I've managed to inspire some of you to get excited about TL-Verilog, after you continue exploring TL-Verilog and maybe doing some more training about TL-Verilog and becoming more comfortable with it, there are various projects that are ongoing. If you look in my GitHub repository, there's TL-Verilog projects. So this outlines a couple opportunities for open source contribution to the TL-Verilog ecosystem. I showed you the Mandelbrot example where we're using FPGAs in the cloud to accelerate web applications. This is a completely new model of computation that was not possible even 5 years ago in any real way. And I've done a lot of work with these cloud infrastructure to make the FPGAs that are, very powerful hardware resources, but kind of lacking in software ecosystem to utilize them in this manner. I've done a lot of work to enable that and that's used by Fractal Valley. So you can work with that infrastructure or even with Fractal Valley. There's also a project called Warp5, which is a RISC-V CPU, and its claim to fame is kind of the level of configurability and flexibility that we get by doing the modeling in TL-Verilog. So this is the repository for Warp5, and this was a poster from a conference. So basically Warp5 uses the mechanisms that we commonly use with TL-Verilog for hardware construction to allow you to configure your design, even as far as what instruction set architecture do you want to support. So this is not even specifically RISC-V, it's CPU architecture, and you can choose RISC-V or choose MIPS and implement yourself a core. You can configure the staging of the pipeline and the bucketing of the logic using the timing abstraction, but now in a parameterized way. You can choose the branch predictors, etc. And then construct your TL-Verilog code, compile your TL-Verilog code. You can do all the development inside Makerchip and sort of end up with your microarchitecture out of that. So there's opportunities to work within that once you've gotten fully ramped up on the various capabilities. There are opportunities to work with the visualization capability that's being rolled out. And maybe I didn't even fully show this. I thought I did. Where we're visually representing our simulation. And I can kind of wrap up by showing some other examples of visualization. So this is a circuit that's sorting numbers, and so basically these numbers are coming in randomly, and the hardware is through various stages of computation sorting those numbers and producing a sorted list in the end. And we can see using the visualization various vectors of numbers being presented to this network and how that network is sorting those values over time. And we can see as I'm doing that in the waveform viewer which cycle we're representing. And you can see how it's much easier to understand what your circuit is doing with this visualization than it is by slogging through the waveform to find values and pick out the right cycles and so on. Some other examples. This one is a simple visualization of a ring network where the ring is sending packets. We're sending packets around the ring. And you can see the packets marching along. There's sort of this ring structure that's not depicted, but we can see the transactions moving around the ring as I simulate. So they're, piling up in FIFOs to issue into the ring and marching around the ring to their destination. And again, you can see how this is much easier to understand what's happening in simulation than looking through a waveform. Let's see, a couple other examples I pulled up here. So this one's a little fun. This is one that I did with my kids. So this is a circuit that's implementing a maze solver. So this maze is kind of fun. It's based on you're a frog. Every actually, let me jump ahead here. Not sure how far. So you're a frog, and your frog jumps to get to the exit, but he jumps 2 spaces at a time. So I can't actually get through this hole to get to the exit lined up properly without taking a number of other actions here. So I have to line myself up properly so I can go through this path to line myself up properly vertically and then jump back. So this circuit is actually solving the maze and then marching the frog through that solution. So that one's kind of fun. And if I jump back to cycle 0, I can see how the algorithm is figuring out the solution to get to the exit by tracing things backward to try to get to the frog's position. And finally figuring out the solution and marching through. All right, so you can see how there's, lots of fun opportunities to visualize what you're doing. You can get a sense at this point of where this technology is going to, really change the way we view circuit design and how we view the circuit design process. Just looking over at the chat, what is the use of TL-Verilog and VLSI? I mean, TL-Verilog is up-leveling the game for Verilog. Right, so it's the new modeling approach, and anywhere that you're using Verilog in the design process today, you can use TL-Verilog. Since I do have a couple minutes here, I will give you a slightly clearer picture of that. So we can see in this help pane here how the flow actually works inside of Makerchip. You edit your code, send that off to the server. This is the macro preprocessing step I mentioned for code construction, hardware construction. That goes through Sandpiper, which is processing your TL-Verilog code into Verilog code. And that's sending all this information back to your browser. That Verilog code gets simulated in an open source logic simulator called Verilator. And that so that compiles your model and simulates your model, producing a waveform that again goes back to your web browser. And all of these tools are generating a log. So that's the compilation flow. So you can see how transaction-level Verilog is implemented as a pre-processing step in front of Verilog. And then you can connect with any Verilog-based tool stack downstream of that. All right. So I think I'll end things here. Again, if you're interested in learning more, you've got these various resources at redwoodeda.com or within Makerchip, makerchip.com. And you can poke around my GitHub repository for, or my GitHub repositories, plural, for various project ideas. And, feel free to connect with me. You can contact me through the Redwood EDA site if you don't have my email address. All right. If there are any other questions, go ahead and drop them in chat. Otherwise, we're all done here. And I'll give it back to the organizers.
Oh, hi, Steve. Yeah, thanks a lot. And maybe, we're waiting for maybe a few more questions. I can ask some. Is this, I think I see a question right now. Is this moving towards the industry design flow? Like, for example, you just showed right now they're using Sandpiper. So like, for example, right now people who are using RTL-Verilog design flow, do they all need is like the Sandpiper in between and then RTL to GDS is complete, or is that something you have to customize it?
Yeah, I mean, as I said, and is my screen still sharing? It looks like it's not. Are you seeing the screen?
Yeah.
Okay.
Your sharing is on. You can see it.
Okay. So I forget which Makerchip window I was in here. Yeah, here. So as I said, the processing of the TL-Verilog is all pre-processing. It all becomes Verilog. Right. And anything that you can do in pure Verilog modeling, you can do with TL-Verilog. In fact, even with TL-Verilog, it's a language extension to Verilog. You can even have sections of code that are just system Verilog. This is a tag that sort of is an indication to the Sandpiper tool or whatever tool is pre-processing your TL-Verilog that, don't touch this code. This is just system Verilog, just pass this through. And it does have macro pre-processing. These are macros that will get expanded. But other than that, it's just system Verilog. So you have complete control of your Verilog. TL-Verilog is just an easier way for you to generate that Verilog code and manage that Verilog code. So anything that you can do with Verilog today, you can extend with support for transaction-level Verilog.
Okay.
So yes, it's appropriate for, there was a question in chat about, how many nanometers is it appropriate for? Anything. I mean, anything you do with Verilog, you can do with TL-Verilog.
Now, are there any applications where you would not want to use TLV and just stick with FTL, or?
I mean, there are folks who just enjoy pain. If you are one of those folks, use Verilog.
All right, that answers that question. So I guess never. So what's the I mean, who's maintaining it now? Is it like it's not a IEEE standard now, or is it a consortium based, or is it?
No, I mean, it's still small scale. It's
okay.
still driven primarily by Redwood EDA, and the open source open source community is becoming more and more active, but still, still very much in the early stages.
Early stage, okay. Okay, so this is
it has yet to.
Sorry, this is a creation of Redwood EDA, right? It wasn't part of another.
Yeah, for the most part. I mean, originally there was. It's based on technology that was an initiative of Intel, and then it sort of branched out into its own thing and became Redwood EDA and so on. But it is, it is very much in its infancy and sort of proving itself in the industry, which is, maybe a source of hesitation for some folks, but also a very exciting time to be involved in it.
No, absolutely. I mean, just the fact that it looks like now the competition is going down the age lane. So you have 12-year-old, and then I guess the 11-year-old is trying right now, and 10-year-old. So that's
yeah, it's very interesting that there's sort of the two facets of it, right? So since we had to crack open Verilog to incorporate all these very powerful language capabilities, that gave us an opportunity to also clean up the language. So it's got this characteristic that it's much more, it's much easier to learn. You guys were able to, even in this short workshop, do some coding exercises that you wouldn't have been able to do in Verilog. So it's much more approachable, much more appropriate for learning about hardware and helping to bring down things to an earlier point in the education. And on the other extreme, it's very, very powerful for very complex, sophisticated microarchitecture modeling.
Right. And yeah, that's probably a segue to was my next question. Like, I know you're quite involved with the education side. Is this something you are actively working with universities and colleges for including in the curriculum, or is that
yeah, definitely. So I'm definitely actively working with universities, again, in the early stages. So I've done a lot of guest lecturing in courses. There's a handful of professors that have, taught a class or two on their own, and are trying to work toward TL-Verilog being a core part of their curriculum. But I am learning how, industry is extremely sluggish. Academia is not as sluggish, but I'm learning that they are sluggish as well. There's the whole curriculum, not just an individual course to re-steer. So it is taking time, but making good progress to get some traction with academia as well.
And what's the best way to jump in? Just follow some of your materials you already have in Makerchip and Redwood EDA to get some. Okay.
Yeah, I think the best starting point is the tutorials inside Makerchip, and then the various materials at in Redwood EDA. And
you have a lot of great visualization tools. So people who already have a flow, like you're saying, they have RTL to GDS flow, and they want to integrate TL-Verilog in it. Because your tools for visualization seems to be in the Makerchip platform, but can we put that in in the flow as well, in the design flow, or that?
Yeah, I mean, one thing that we're actively doing right now that should be rolling out, you know, within 2 weeks or so, is the ability to launch Makerchip from your desktop. So if you have an existing environment that you're working in with all, you know, Xilinx, FPGA tool stack and everything, but you want to do your editing with TL-Verilog, you know, to avoid the awkward cut and paste between your desktop environment and the Makerchip platform, we'll have the ability to launch Makerchip from your desktop so that it runs similar to just running a local desktop application. So you can use that as your editor in whatever environment you're working in with other industry tools.
Okay, great. That's all I have from my side. I don't know if you...
So there's a question here. So currently TL-Verilog is supported by Redwood EDA Sandpiper tool, and there is an open source TL-Verilog compiler. It doesn't get much use because the Sandpiper compiler is freely available for academia, for open source development. But there is that option out there.
All right. Well, thanks a lot, Steve, for taking time for this workshop. You know, always enjoy your workshop. They will design. I'm sure the participants enjoyed it. It was very smooth. I was a little worried about, you know, maybe, you know, a lot of participants being the traffic, but it looks like went smoothly. People were able to do it. So
good. Yeah, I'm happy to be a part of it.
Yeah, thanks. And I'm sure, you know, we'll be getting engaged with a lot of your training programs you have at one point in the time or the other.
Great. Thanks so much.
All right. Thanks. Thanks, Steve. Have a good day.
You too.
Bye.
All right. Bye, everybody.
Bye, Steve.
Okay, sorry, just a quick announcement for tomorrow will be, I think the program schedule is gone. Tomorrow, 10 a.m. Sharp will start, maybe join in around 9:45. First talk will be by Rohit Sharma on the Tiny ML application, and then followed by 11:30 will be Atul Bhargav's talk from ST Microelectronics, and then we'll have a 5 p.m. tutorial as well on the open source flow. So we'll blast some program schedules again. You know, we'll see you tomorrow at 10 a.m. Okay, thank you. Thank you, everybody.
Thank you, everyone.
Puneet, you wanted to add something?
No, sir. I'm good.
Okay. All right, great. Okay. Thanks, everyone. We'll stop here for now. See you tomorrow morning, 9:45.
Bye, everyone. Bye-bye.